Okay, years ago when my kids were small, we went to Yellowstone National Park. And of course, one of the highlights was to see Old Faithful. Suppose we got there just as the guys are finished erupting. Now, I had little kids then, and I wanted to know how long it was going to be before the next eruption because the kids were going to get restless waiting. According to the data, the shortest interval between eruptions was 47 minutes, and the longest was 113 minutes. That was a big difference when you've got 3 and 4-year-olds. There's two clear peaks at 60 and 90 minutes. When should we come back? Well, looking at the distribution of a single variable doesn't tell us everything we want to know. What if at certain times of the day it erupted closer to every 60 minutes, while at other times of the day it erupted every 90 minutes? Well, that would help us figure out when we wanted to come back. So knowing both variables would help us to make a better prediction as to when the next eruption would be. So why do we study the relationship between two variables? Knowing the distribution of a single variable often doesn't tell us everything we need to know. Sometimes we need to compare two or more variables to get a complete picture. Most statistical studies examine data on more than one variable. Fortunately, analysis of several variable data builds on the tools we use to examine individual variables. The principles that guide our work also remain the same. We're going to plot the data, then add numerical summaries. Look for overall patterns and deviations from those patterns. And when there's a regular overall pattern, use a simplified model to describe it. For example, an insurance group reports that heavier cars have fewer deaths per 100,000 vehicles than lighter cars do. We think that car weight helps explain accident deaths. It's also been found that smoking influences life expectancy. In these relationships, the two variables play different roles. Accident death rate and life expectancy are the response variables of interest. Car weight and the number of cigarettes smoked are the explanatory variables. So what's the difference between explanatory and response variables? A response variable measures an outcome of a study, while the explanatory variable may help explain or influence changes in the response variable. For example, to study the effect of alcohol on body temperature, researchers gave several different amounts of alcohol to mice. Then they measured the change in each mouse's body temperature 15 minutes later. In this case, the amount of alcohol is the explanatory variable, and the change in the body temperature is the response variable. When you do not specify the values of either variable, but just observe both variables, there may or may not be an explanatory and response variable. Whether there are depends on how you plan to use the data. Okay, so here's an example. Julie wants to know if she can predict a student's weight from his or her height. Information about height is easier to obtain than information about weight. Jim wants to know if there is a relationship between height and weight. For each student, identify the explanatory variable and response variable if possible. Julie is treating a student's height as the explanatory variable and the student's weight as the response variable. Jim is just interested in exploring the relationship between the two variables, so there is no clear explanatory or response variable. Okay, so now would be a good time to stop and check your understanding on page 144, and I'll be right back with you. Okay, so how does beer affect the level of alcohol in our blood? The legal limit of driving in all states is 0.08%. In a study, adult volunteers drank different numbers of cans of beer. 30 minutes later, a police officer measured their blood alcohol levels. So we're identifying the explanatory and response variables. The explanatory variable is the number of cans of beer. The response variable is the blood alcohol level. Okay, in this second problem, there are two explanatory variables, the amount of debt and income. The response variable is the stress caused by college debt. The most useful graph for displaying the relationship between two quantitative variables is a scatter plot. A scatter plot shows the relationship between two quantitative variables measured on the same individuals. The values of one variable appear on the horizontal axis, and the values of the other variable appear on the vertical axis. Each individual in the data appears as a point in the graph. So how do you know which axis to put which variable on? Always plot the explanatory variable, if there is one, on the horizontal axis. That's the x-axis of the scatter plot. As a reminder, we also call the explanatory variable x and the response variable y. If there is no explanatory response distinction, either variable can go on the horizontal axis. So how do we know which variable to put on which axis? Plot the explanatory variable, if there is one, on the horizontal axis or x-axis. We call the explanatory variable the x and the response variable the y. What is the easiest way to lose points when making a scatter plot? Forget to label your graphs. If you forget to label your graphs, you're going to lose points. That includes the proper labels. Including the proper labels is more important than graphing each point in precisely the right place. So you're going to lose points if you don't label your graphs. Now, another thing to remember is that there's the only choice for displaying the relationship between two quantitative variables is a scatter plot. For a single variable, there are many choices. You could use dot plots, histograms, box plots, and stem plots. But for two variables, a scatter plot is what we use. So what's the difference between the axes of scatter plots and other graphs? Scatter plots have two quantitative variables that they're checking the relationship of. One axis represents one variable, the other axis represents another variable. Other graphs are just for single variables. They're not comparing two variables. So we're going to make a graph here. The table below shows the data of 13 students in a statistics class. Each member of the class ran a 40-yard sprint and then did the long jump with a running start. Make a scatter plot of the relationship between sprint time in seconds and long jump distance in inches. When making a scatter plot, you have to decide which variable should go on each axis. Label and scale your axis and plot individual data values. Okay, so when we make a scatter plot, we have to decide which variable should go on which axis. Well, we're going to say that the sprint is our explanatory variable and the long jump in inches is our response variable. Notice that we're not starting at 0 here. That wouldn't make sense, 0 time. So what we are going to use is our sprint time in seconds, and each of these goes up by the same unit. The units of the x-axis and the units of the y-axis do not have to match, but the intervals between each of the values of the x have to be the same, and each of the values of the y have to be the same. So just make sure that the scale of each axis is consistent. Okay, so this is sort of what your graph should look like. Make sure that you have your axes labeled. Once we've graphed our scatter plot, our data on a scatter plot, then we have to interpret the scatter plots. So what four characteristics should you consider when interpreting a scatter plot? Well, you're going to look at the direction, whether it's going from left to right, down from left to right, or going up from left to right. The form, that would be whether it is a slightly curved or whether it is fairly straight. The strength of the relationship, that's how clear the points follow that form. And then, of course, we're going to look for outliers. Okay, so let's go over the characteristics. The direction, a clear direction, well, does it move from upper left to lower right? That's a negative association. Or from lower left to upper right? That's a positive association. The form, is it curved or follow a relatively straight line? 3, the strength. How closely do the points follow that pattern? And 4, outliers. That's any individual value that falls outside the overall pattern of the relationship. The strength is probably one of the hardest ones to figure out. When you're trying to identify outliers in a scatter plot, you need to look for points that fall outside the overall pattern of association. Unlike with distributions of a single variable, there isn't a specific rule for identifying outliers on a scatter plot. Okay, here's AP tip. On the AP tip, if you're asked to describe a scatter plot, you're expected to discuss the direction, the form, and the strength of the association in context, as well as identify any possible outliers. Similar to SOX, which was shape, outliers, center, and spread, we do have an acronym for this as well. It's DOS. Okay, so DOS stands for direction, outliers, form, and strength. When discussing the form of a relationship, don't let one or two unusual values influence your description. For example, if covering up one value makes the form go from nonlinear to linear, you should call it a linear association with an outlier. That is especially true for small sets of data. Okay, does strong association between two variables indicate cause and effect relationship? No, it does not. Does not imply that at all. For example, did you know that AP Calculus is causing global warming? As the number of AP Calculus exams has grown over the years, so has the average global temperature. Obviously, they're seeing a correlation, but is that cause and effect? No. What about, did you know that eating ice cream causes people to drown? In the months with higher ice cream sales, there are also higher numbers of drowning deaths. No. This does not indicate a cause and effect relationship. So just because you see a strong association between two variables, it does not indicate cause and effect. Now would be a good time to turn this off, to pause it, and check your understanding on page 149. Be back later. Okay, the relationship is positive for number one. The longer the duration of eruption, the longer the wait between eruptions. One reason for this may be that if the geyser erupted longer, it expended more energy, and it will take longer to build up the energy needed to erupt again. So what form does the relationship take, and why are there two clusters of points? Okay, so what's the form? The form is roughly linear with two clusters. The clusters indicate that in general there are two types of eruptions, one shorter and the other somewhat longer. Okay, so